So in the last lecture we have dealt with ferromagnetic substance. In this lecture we will deal with paramagnetic and diamagnetic substance. So let us deal with first a paramagnetic substance. So difference between para and ferromagnetic substance is that ferromagnetic substance creates a very strong atomic magnet, and paramagnetic substance creates a very weak atomic magnet. And here inside the paramagnetic substance there are no such domains, just the atomic magnets are randomly oriented like this. They go haywire actually. In domains there are certain groups which point towards a certain direction, but here it's just randomly points here and there, and forms closed chains actually like this. Now here if you apply an external magnetic field, rather this B external, which was equal to mu 0 into H. Remember that na? H is the intensity of the magnetizing field, H, or we call it the magnetizing field intensity. So if you increase this external magnetic field, some of the atoms will align itself while most of them won't align. So due to the sum of the atoms, there is a slight atomic magnetic moment inside the magnet, right? So this is inside you have this B atomic, and this B atomic is actually a small fraction of the B external. Here in this case, here what happens, this B atomic is proportional to B external. That means more B external, more of the atoms will obey the torque produced by B external and point in the direction of B external. So more B external, more will be B atomic. So B atomic is proportional to B external. Now this proportionality constant is the susceptibility. So I'll write it like this: B atomic equal to this times B external. So this constant is known as susceptibility, or rather magnetic susceptibility of the paramagnetic substance. So B atomic is equal to, again B atomic is mu 0 into I. What was I? I is the intensity of magnetization, that is magnetic moment per unit volume. I, intensity of magnetization, that is magnetic moment per unit volume, obviously atomic magnetic moment per unit volume. Okay, so mu 0 into I is equal to B atomic. So therefore if you substitute this, B atomic is mu 0 into I equal to susceptibility into B external, mu 0 into H. So therefore I is equal to susceptibility multiplied by H. Remember, in paramagnetic in ferromagnetic substance, I is not proportional to H. It's the relation is very complicated. It follows a curve, right? It follows a curve, and even for one value of H you can have three values of I. So that's a strange curve, but for paramagnetic it's quite straightforward like this: I versus H. This is not drawn to scale. If it is drawn to scale, then it will be very small. Say for example, I'll tell you, for magnesium susceptibility is 1.2. for oxygen susceptibility, not 1.2 radar, for oxygen susceptibility is 0.18 into 10 to the power minus 5. So see how small it is. And for magnesium, susceptibility is equal to 1.2 times 10 to the power minus 5. So it's very very small. If the graph is drawn to scale, this angle theta will tend to 0 always. So you can't draw a curve actually. So it is not drawn to scale. Okay. So these are paramagnetic substances, and inside paramagnetic, magnetic field is equal to obviously B external plus B atomic. So that is B is equal to mu 0 H plus mu 0 I, that is mu 0 into H plus I, or we can write mu 0 into H plus susceptibility into H, that is mu 0 1 plus susceptibility multiplied by H. So this 1 plus susceptibility is mu R. Mu R is known as the relative permeability. Relative permeability of the paramagnetic. And obviously mu 0 is permeability of free space, so mu 0 times mu R is mu. This is absolute permeability. Absolute permeability of the paramagnetic. So that is all about paramagnetic substances. Remember the formulas and susceptibility and all this. Now there are certain substances known as diamagnetic substances. So in a diamagnetic substance, the atomic magnetic moment is equal to 0. So that means, so you can compare it with a loop, a current carrying loop having no current. That is, the atomic current is equal to 0. From Faraday's law and Lenz's law, so that we'll learn in our next chapter, electromagnetic induction. You know that if you have a coil, current carrying coil, see the basic theorem in very easy words, I can express Faraday's law that the current, so the closed conducting coils head the change in magnetic flux to this. So that is all. That is Faraday's law in a nutshell. So if you have a, say if you have a conducting loop this way, you have a conducting loop, and you know the law that it won't tolerate any, it will oppose to tolerate any change in magnetic flux through this closed coil. So if you send in magnetic field, then it will make current flow in the opposite direction. I mean opposite in which sense? That it produces a magnetic field in this direction. So it tries to negate the change in magnetic flux. So B dash. B dash is the magnetic field created due to the current. So this I is the induced current. Induced current you will learn in more details in our next chapter, EMI. So suppose there are diamagnetic substances, so they have absolutely no magnetic property, Now, if you keep a diamagnetic substance in an external magnetic field, then what is going to happen? The say, suppose I draw this a loop, current carrying loop. Suddenly, if you bring in this B external, the current carrying loop will oppose, and the current here will flow in such a direction that it will produce this atomic magnetic field in opposite direction. It was like the atom was like a coil with no magnet, I mean no current rather, but after exposing it to the external magnetic field, a current flows in the coil. Now this diamagnetic substance happens as there are paired electrons, so the resultant magnetic moment of such atoms are zero. Okay, so if you keep, so inside this, so we can write B atomic is equal to susceptibility multiplied by B external. Now for diamagnetic, for the diamagnetic substance, susceptibility is negative. It's a small negative number. For example, nitrogen is diamagnetic. It has a susceptibility of minus 5 times 10 to the power minus 4, like this. So if you draw the curve I versus H, I versus H is same as B atomic versus B external. So this will be the graph, like, as the susceptibility is negative here. So that is all about diamagnetic substance. Remember, all matter have a diamagnetic property because Lenz's law is a true law in nature. So even the paramagnetics, ferromagnetics, that have a diamagnetic property. Okay. And one thing I will discuss, as the temperature is increased, as temperature is increased, so the intensity of magnetization decreases, intensity of magnetization due to randomization. So the susceptibility is given like this, some constant divided by T, temperature. And this is the Curie's law. Okay. This law is true for a paramagnetic substance. For a paramagnetic substance. Okay. Now I'll draw 3 substances in external magnetic field and see how these will behave. Pardon. So this is the external magnetic field. Now in one of the cases, the external magnetic field is highly condensed inside this substance, and in one more curve the external magnetic field is, it goes slightly inside. That means, see, the more close are the magnetic field lines, the stronger the magnetic field is. And in another case it's like this. So this is case 1, case 2 and case 3. In case 3 you find B, that means, see, as the magnetic field lines are lesser closely packed, so it's a weaker field. So inside the substance in case number 3, magnetic field is weaker than that outside. So this is diamagnetic, this is paramagnetic, and the extreme left one is ferromagnetic. So that is all about ferromagnetic, paramagnetic and diamagnetic substance.